What if I told you that the reason you recognize your mother's face, drive a car, or even understand the sentence I'm speaking right now all boils down to a mathematical imitation of this single line of code? Output is equal to activation multiplied by dot product of weights and inputs plus bias. It isn't magic. It isn't a sci-fi. It's math. Today, we aren't just learning a concept. We are looking at the atom of artificial intelligence, the perceptron. Hi everyone. Welcome back to Sumantra Codes. I'm Sumantra. I have spent over 20 years in the software industry building systems that scale and debugging code that, let's be honest, sometimes felt like it had a mind of its own. But nothing, and I mean nothing, is as fascinating as deep learning. If you have been following my Python series, you know we usually dive straight into the IDE. We are putting the keyboard aside for a moment and build a massive mental model. We need to bridge the gap between biology and linear algebra. We are going to break down weights, biases, and the infamous dot product in a way that will make you say, oh, that's how ChatGPT actually works under the hood. This is the foundation of everything. If you understand this, you understand the future. Let's dive in. To understand the artificial neuron, we first have to respect the original architect, Mother Nature. Your brain is a massive parallel processor made of approximately 86 billion neurons. That is a staggering number. But if you isolate just one of those neurons, the mechanism is actually surprisingly understandable. It's not performing complex calculus. It's performing a simple aggregation of signals. Let's look at the three critical components of a biological neuron. First, we have the dendrites. Look at these branch-like structures extending from the center. These are listeners. Their entire job is to receive electrical signals, chemical messages from other neighboring neurons. Think of them as the ears of the cell. Second, we have the soma, or the cell body. This is the processor. It takes all those little electrical zaps coming in from the dendrites and sums them up. It accumulates the charge. And third, we have the axon. This is the speaker. If the charge in the soma gets strong enough, if it crosses a specific threshold, the neuron says fire and shoots an electrical pulse down the axon to the next neuron in the chain. This firing event is called action potential. And here's the secret. It is binary. The neuron either fire or it doesn't. It doesn't kind of fire. It doesn't fire a little bit. It's all or nothing. Now travel back to the time with me to 1957. A psychologist named Frank Rosenblatt is looking at this biological process and thinks, I can build a machine that does this. He called it the Perceptron. He didn't build it in Python. He built it with actual wires and motors. But the logic was same. He wanted to map biology to math. So in our code, the dendrites become our inputs, which represents the vector x. The synapse strength, the connection between neurons, becomes our weights, represented as W. The soma become weighted sum function, denoted by sigma, symbol sum, and the action potential, that becomes our activation function. It is a beautiful simplification. We stripped away the messy biology and kept the pure logic. But how does this math actually make a decision? How does it think? That brings us to the most important concept in all of neural networks, the weights. Let's really drill down the weights, or W. When people talk about training a model or downloading a model, what they are actually talking about a giant file full of weights. The weights are the brain. Imagine you are a perceptron. Your job is simple. You need to decide, should I go to the music festival this weekend? You have three inputs coming in from your friends or the dendrites. First, input 1 is the weather good, or 1 for yes, 0 for no. Input 2 is the ticket expensive, value 1 for yes, 0 for no. Input 3 or x3 is your favorite band playing, value 1 for yes, 0 for no. Now be honest with me. Do all these factors matter equally to you? Probably not. If you're a massive fan of the band, that third input matters a lot. If you're broke, that second input, the price, matters a lot, but in a negative way. If you're tough, maybe you don't care about the weather at all. This caring is exactly what a weight is. A weight represents the strength of the connection or the importance of the input. Let's assign values. Weight for weather, W1, let's say is 2. It matters a little. Weight for price, or W2, let's say its value is -5. A high price is huge negative for you. Weight for band, or W3, let's say it's 10. You really love this band. Mathematically, neuron processes this by multiplying input by the weight, x1 dot W1. Think of what happens here. If the band is playing, which means x3 is 1, and the weight is huge, which means W3 is 10. The result is 10. That is a loud signal screaming go. If the band is not playing, which means X3 is 0, then it's 0. The signal is silent. This is the core mechanic. The weight allows the neuron to amplify some signals and suppress others. When we say a neural network is learning, we don't mean it's writing new code. We mean it's adjusting these sliders. It is tweaking these numbers. It is figuring out for this specific task, the band input is more important than the weather input. It is learning what to pay attention to. So we have these individual signals. The weather is whispering yes, the price is shouting no, and the band is screaming yes. The neuron has to gather all these conflicting opinions and combine them into a single value to make a decision. This accumulation is the weighted sum. So we have Z equal to x1 dot w1, x2 dot w2, x3 dot w3, and we sum all of them. In linear algebra, we have fancy name for this specific operation, multiplying matching pairs of numbers and adding them all up. It is called the dot product. Now, I want to visualize this geometrically because this is where the intuition clicks. Imagine your inputs are an arrow pointing in a specific direction in space. Imagine your weights are another arrow pointing in a different direction. The dot product tells us how much these two arrows align. If they point in the same direction, the dot product is a huge positive number. If they point in opposite directions, it is a huge negative number. If they are perpendicular or 90 degrees, then the dot product is 0. Why does this matter for AI? Because the dot product is actually a similarity score. The neuron has a weight vector that represents what it wants to see. For example, a cat detecting neuron has weights that look for a pointy ears and whiskers. A spam detecting neuron has weights that look for the words free or winner in the email. When an input comes in that looks like what the neuron is hunting for, the vector align. The dot product explodes. The sum is high. The neuron gets excited. This is why we use dot product. It is a mathematical way of asking, does this input match my pattern? If yes, the score is high. If no, the score is low. So, when you see np dot bracket inputs comma weights bracket close in Python code, don't just see multiplication. See a pattern matcher looking for a match. So, we have inputs, we have weights, but we are missing one crucial piece of puzzle, the bias. The formula isn't just w dot x, it is z is equal to w dot x plus b. Why do we add extra b at the end? Why isn't the weighted sum enough? Let's go back to our music festival example. Imagine the festival is free, so the price is 0. The weather is neutral, so the weather parameter is also 0. And the band is unknown, so the band input is 0. All your inputs are 0. If we only use weights, the math looks like 0.2 plus 0.5 plus 0.10, which is equal to a 0. The total sum is 0. But maybe you are introvert. Maybe if everything is neutral, your default is no, I am staying at home. You have a negative baseline. Or maybe you are super extroverted. Even if you know nothing about the event, you default to yes, let's party. This is what bias is. It is a neuron offset. It represents the threshold that needs to be crossed before the input even matter. A negative bias like -10 means the neuron is skeptical. It needs a lot of positive evidence or high inputs to overcome that negative bias and fire. It's hard to please. A positive bias like +10 means the neuron is trigger happy. It is already halfway to firing before it even sees any data. Without a bias, your neural network is mathematically paralyzed at the origin. It can rotate the line, but it can't shift it. By adding the bias, we give the model the flexibility to fit any data anywhere on the graph. So in simple terms, weight control the slope, bias control the position. Okay, we are almost there. We have calculated our weighted sum and we have added our bias. Let's say the final number comes out to 5.2. Now, is 5.2 a yes? Is it a cat? Is it a spam? Computer needs certainty. They usually need binary output or a probability. This is the job of the activation function. It takes that raw number of 5.2 and squashes it into a format we can use. In Frank Rosenblatt's original Perceptron, he used the simplest logic possible, the step function. The logic is essentially, if the sum z is greater than 0, the output is 1. And if the sum z is less than or equal to 0, the output is 0. This simple check turn our linear math, which is just a continuous number like 5.2 minus 1.8, 100.5, into a non-linear decision. And this word non-linearity is the holy grail of deep learning. Why? Because the real world is non-linear. Think about studying for an exam. If you study for 1 hour, your grade goes up a bit. If you study for 10 hours, it goes up a lot. But if you study for 100 hours, your grade doesn't go up 100 times more. It plateaus. You hit a limit. That is a curve, not a straight line. The activation functions allow neural network to understand these curves. Without it, a neural network, no matter how deep, is just a fancy linear regression model. It collapses into a straight line. Now, modern networks use fancier functions like Sigmoid, which gives probability between 0 and 1, or ReLU, which is the current industry standard, but they all serve the same purpose. They decide if the neuron opinion is stronger enough to matter. Before we wrap up, I have to tell you the dramatic twist in the Perceptrons history. In 1969, Marvin Minsky and Seymour Papert published a book that almost killed AI research for a decade. They proved that a single perceptron has a fatal flaw. It can only solve linearly separable problems. It can separate a group of dots if you can draw a single straight line between them. But look at this pattern. This is XOR, or exclusive OR problem. The red dots and blue dots are diagonal from each other. Try to draw one straight line to separate the red from the blue. You can't do it. It's impossible. This realization caused AI winter. People thought, if it can't even solve this simple logic puzzle, it's useless. But they were wrong. The solution wasn't to abandon the perceptron. The solution was to stack them. If one line can't solve it, use 2, use 100, or use a billion. And that is what gave birth to the multi-layer perceptron or deep neural networks we use today. We have covered a massive amount of ground today. We deconstructed the brain of a machine. Let's recap the core architecture so it sticks. Weights. These are memories. They determine the importance of the input. They are the sliders that the machine adjusts during the learning. The dot product. This is the engine. It calculates the similarity between the input vector and the weight vector. The bias. This is the personality. It sets the threshold for activation, allowing the neuron to shift its decision boundary. The activation function. This is the judge. It introduces nonlinearity and decides whether the signal is strong enough to fire. And that brings us back to a single line of code. It's elegant, it's powerful, and it is the building block of everything from Siri to self-driving cars. But here is the thing. Understanding the theory is a step 1. Step 2 is building it. If you want to see me actually code this perceptron from scratch in Python, no PyTorch, no TensorFlow, just raw math and logic, I need you to let me know. Drop a comment below saying build the brain if you want a follow-up tutorial. If you got value from this deep dive, please hit the like button. It really helps the YouTube algorithm to find other engineers like us. Don't forget to subscribe the ring bell so you don't miss the coding session. I'm Sumantra. This is Sumantra Codes. And remember, keep coding and keep learning. I'll see you in the next one.